Welcome back, everybody. This is going to be the final of 3 parts in my lecture series on solving systems of linear equations. If you haven't seen the first 2 videos, please go back and watch those now, as you're going to need that information for this video. Because in this one, we're going to solve larger systems of equations, that is, in 3 variables. Let's get started. A linear equation in 3 variables has the form ax plus by plus cz equals d. And the picture of this graph, now because we have 3 variables, we would need a 3-dimensional graph, looks like a plane. Let me show you a picture. Now, you will not be responsible for graphing anything in 3D. In fact, we don't even typically talk about this until Calculus 3 or multivariable calculus. So don't worry about this part. This is more just so that we can all kind of see what's going on under the hood here. Let me see if I can collapse this. Okay, so this is the equation at 1x plus 1y plus 2z equals 11. This would be a linear equation in 3 variables. And as you can see, it forms a plane in 3D. We're now, the red line you're seeing down here, this is the x-axis, the green line is the y-axis, and the blue line is the z-axis, right? So we can think about this as, when I look at it this way, this is 2D, right? This is our normal plane, x-axis, y-axis, and now coming out of the plane is our z-axis. Okay, let's get back to solving these systems. So, a system of 3 equations and 3 variables looks like this. In order to solve for 3 variables, we need 3 equations. In order to solve for 2 variables, we need 2 equations, 4 variables, 4 equations, and so on. So, to do that, we use a combination of substitutions and eliminations. So, how do I do that? Well, let's look at this system. I like to number my equations. So first things first, in this big ugly system I have down here, I'm going to graph label 1, 2, and 3. And what I notice right off the bat is that equations 1 and 2 already look like a prime setup for an elimination for both x and y. Notice if I multiply equation 2 through by -1, that x and y will have opposite coefficients. So that's exactly what I did for this first step. I multiplied through by -1 and then added them together. And because that eliminates x and y, I have a single variable equation for z, which gives me z equals 3. The next step then is, now that I have one of my variables, I'm going to plug it back into my system and just see what happens then. So when I plug this back into my system, notice everywhere I had a z, I now have the number 3. I can simplify it down to these 3. And notice equations 1 and 2 now are the same equation, just by coincidence here. So I can't really do stuff with these guys since they're the same equation. Instead, I'll have to look between 2 and 3. And I notice again, this is already set up pretty nicely for an elimination on x. If I just multiply equation 3 by -1, I can add 2 and 3 together to eliminate x. So that's what I did in the next step. And this gave me a single variable equation for y, which gave me y is also 3. Now that I have 2 of my variables, y and z, I can use them both in one of my equations to get x. I used equation 1, that x plus y plus 2z equals 11. Or x plus 9 is 11, that tells me x is 2. So the solution to this system is x, y, z, or 2, 3, 3. But what does that look like in the context of that weird 3D picture we were looking at? Well, let's take a better look. So here, you'll notice I have sketched the graph of equation 1 in blue, equation 2 in green, and equation 3 in this gold color. And our solution A is the point where all 3 of those planes intersect each other. think back to when we were looking at two equations. We just had those two lines, and where they crossed was the solution. When we have three equations, it's where all three of the equations cross that give us the solution. But I've got one more for you guys to try. Go ahead and pause the video here to see if you can tackle it on your own. If you need a hint, let the video play a little bit longer. Ready for the hint? I tried elimination on equations 2 and 3 because I saw the z variables are all ready to go. So all I need to do is add equation 2 to 3, and I get this guy, 4x plus 3y equals 4. From here, I just need to solve the system of two variables and two equations, equation 1 and equation 4, this new guy that I've just made. Go ahead and pause the video here to see if you can take it from here. The solution that I found was 1, 0, -3. Here's how I did that. After the hint, I had this system between equations 1 and 4. I used substitution to solve this system. I wrote y equals 2 minus 2x and then substituted that into equation 4, giving me this equation, which when I solve for x gives me 1. I plug this value of x back up into here to get y as 0. Now that I have x and y, I go all the way back to my original equation to get me z is -3. In this video, we saw how to solve systems of 3 equations with 3 variables. That's going to do it for my lecture series on solving systems of linear equations. Catch y'all in the next one.